I don't have access to week two yet.
Oh, sorry, I haven't, yeah, I didn't update that picture. I'll update that when I get back.
Okay. Thank you.
Yep.
Get some water from the fountain. Nice. Like what? So the X. Explain them. Yeah, so you would just leave that. So, copy.
Sincerely.
I'm just gonna write it down. Right.
It's B is equal to B two plus B three. What's the question next one? Q two. Q two, Q three, and B two is the B three. Yeah, so we just change it. So it's just Q two or Q three is Q one. It's gonna be two plus three.
Just gonna change this equation.
So Q because you need Q two and Q three. So you need Q two and Q three. Two.
Yeah. I'll measure the power rates. 18. Being
Q from Q, you have A already. Solve A, it's all. Issue for you.
All right, it's 3 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. Okay, so today we're starting something new. Although I guess that's not new. This summer's going so fast. Every day we're doing something new. So today we're going to be talking about fluid kinematics. So this topic itself is interesting. There's not really much in the way of examples here or applications. This is kind of more set up for what we're going to do after this. So today's going to just be a lot of concepts, a lot of conceptual understanding, not really any examples. So it's kind of a good one to have now, just because I know everyone's kind of preparing for the midterm. And so I think probably tomorrow after the midterm, we'll see kind of the first applications of this theory. But there's kind of a lot to set up in the meantime. So that's kind of the goal for today. Okay. So just a reminder, today everything we cover today is not going to be on the midterm. So the cutoff for the midterm was yesterday at 5:50 p.m. So only up to Bernoulli equation is going to be expected for you guys tomorrow. But hang on to this stuff. So this stuff is important, and we'll get to this stuff on the second. Okay. Okay, and also as a reminder, remember tomorrow is our first midterm exam, June 4th. It'll take place in the first 80 minutes of the lecture. So it's going to take place between 3 p.m. and 4:20 p.m. So please be here in person. There are no plans to offer the exam virtually. So for those of you on Zoom, I don't mind you guys being on Zoom for the regular lectures, but for the exams, you do have to be here. Remember, the things you can bring for the exam are your writing utensil, your calculator, and one 8.5 by 11 sheet of notes. Remember, you can write or type the note sheet. You can write on both sides. Anything on there is fine with me. You can put just your notes, or you can put example problems, whatever you want. Only thing you can't have is just the exam answers. Okay. All right. So I think that's all my announcements. Any questions I can answer before we get started for today?
homework tonight.
Homework, yes, thank you. Yes, remember homework 2 is due tonight as well, so that's on the Bernoulli equation. So I know that was a very quick turnaround, but hopefully it's still fresh in everyone's mind just because we finished talking about it yesterday. I will post a solution tonight, probably around, depends on when my son goes to sleep, but probably around 9 or 10 o'clock tonight. That's probably when I'm posting the solutions. Okay. Just so you have that for your studying as well. All right, any other questions before we begin today? Okay, all right, so let's go ahead and get started. Okay, so the topic for today is what we call fluid kinematics. Okay. All right, so now that we're kind of done with the first midterm topics, first midterm is always kind of just always generally fluid statics and Bernoulli's equation. We're kind of really starting to kind of hit our stride here. So fluid kinematics is kind of really the setup for a lot of the rest of this semester. Okay. Okay, so the whole idea with fluid kinematics, this is kind of our introduction to, I would say, the standard ways to describe fluid flow. Okay. So in that sense, it's quite similar, or it plays the exact same role to kinematics in classical mechanics, right? So before you learn some more advanced topics like Newton's law, momentum, angular momentum, you have to first know how to describe motion, right? So you have to be familiar with concepts like position, velocity, angular position, acceleration, things like that. Okay. So fluid kinematics is the same thing, right? And so in a lot of ways, I think about kinematics as, kind of learning the language of fluids. which sounds silly. I know. That's kind of why I put it in quotations there. But you'll see that there's fluid motion is a lot more complex than solid motion, and so there's a lot of different ways that we can describe it. And even the concepts of just describing just a basic fluid flow is not that simple. It's not that it's not trivial. And so that's kind of what the that's kind of the whole point of this section here is to learn what concepts and what vocabulary and what concepts that we can use to describe the fluid. Okay? But this is going to set the baseline and kind of set the stage for more complex topics and concepts in fluid mechanics. Things like control volume analysis, that's kind of the next immediate thing, to things like Navier-Stokes equations and so on and so on. Okay. All right. So the first kind of topic, or the first kind of concept in fluid kinematics is this idea of the Lagrangian description versus the Eulerian description. So those sound very fancy, just because those are named after people. They're named after ancient Greek mathematicians that first came up with this, or I would say first formalized this theory. And you might think it kind of strange for there to be multiple ways to describe fluid flow, right? Because fluid flow is fluid flow. The fluid's still the same. These are just kind of different ways for us to describe what we're kind of seeing. Okay. Okay. All right. So let's kind of describe what these are. So let's start with some definitions. Okay, so let's start with Lagrangian first. I would say this is kind of the more non-traditional way to describe fluid flow, although this does have its applications at times. Okay. And so the Lagrangian description of fluid flow, mostly concerns itself with tracking individual fluid particles as it goes through a flow. Right. Another way to kind of think of the Lagrangian description is that you're going to look at a fixed amount of fluid mass, right? So one particle is a fixed amount of mass. Although we can generalize this and use the Lagrangian description for a fixed amount of just fluid in general. We're going to tag that fixed amount of mass and then follow it as it goes through a flow. Okay. All right, so visually it looks like this. And so, let's say you have a flow field that looks like this, right? So we have fluid flow that's kind of flowing in this direction. All right, so for a Lagrangian description, you would take a single fluid particle. So let's say we have a particle here that starts right there, okay? So call this P1, okay? Right? And so if we were going to use a Lagrangian description of this fluid flow, we would say we're going to follow P1 as it goes through the flow. So this P1 is going to have its X, Y, and Z coordinates, if we're in 3D, as a function of time. Right? And so we're basically tracking the position of that particle as it goes through flow. Okay. And you can do this for multiple particles as well. Right? So you can have another particle P2, P2 is going to follow a different path. And so let's say we start P2 at a point that's slightly below, right? So this is going to have its own x2 of t, y2 of t, z2 of t. Right, and then you can generalize this even more for more particles. Okay. Now you can see, the Lagrangian description is generally not that efficient because generally a fluid flow consists of lots and lots of particles, not just two. Right. Usually there's dozens and dozens of particles or hundreds and hundreds of particles. So typically Lagrangian is not, this is not the standard way that we use to describe fluid flow. Although it does have its applications. There are certain fluid flow applications or engineering applications where you are interested in individual particles. There's ways to track that. There's an experimental technique called particle image velocimetry, PIV. That's a very popular technique. But I would say in general, most fluid applications, we don't use the Lagrangian description. Okay. And especially if there's any kind of complexity in the flow where the particles can go in lots of different directions. Let's say you have some turbulence involved in the flow, so there's some chaotic motion. The Lagrangian description just is not practical in those cases. Okay. So the standard way to describe fluid flow takes on the Eulerian approach. Or Eulerian, depending on how you pronounce it. I never ever get a straight answer to find out if his name is pronounced Euler or Euler. So I just kind of just swap based on kind of what I feel in the moment. But I'll call this Eulerian. Okay? So the Eulerian description uses the concept of a field to describe fluid properties as functions of space and time. Okay? Right, so we've already kind of introduced the idea of a velocity field, right? So that's what we talked about yesterday. So the standard way to describe that is the Eulerian description. Okay. So the best way that I can think of to illustrate this is, let's say you have a fluid flow situation. And so inside the fluid flow, you're going to put lots and lots of little tiny probes at fixed locations where each probe is measuring what the velocity and pressure is and other quantities as a function of time. So the way to kind of describe this is, let's say we have a fluid flow situation again, right? So we have a velocity that kind of looks something like that, some streamlines, right? So under the Eulerian description, we're going to be putting probes into this flow, right? Okay, so let's say we're putting probes in fixed locations just like this. They don't have to be spaced this far apart. In fact, technically in the land description, there's probes everywhere, at every single location, but I'm just putting spaces in between them just to illustrate. And at each probe location, we are making observations in terms of, what the fluid velocity is going to be, what the density is going to be there, what the viscosity is going to be there, and so on and so forth. Right? So instead of, following the flow, under the layering description, we're just letting the flow kind of progress itself, and we're describing the flow at each kind of individual location. So you can think of it as kind of a more holistic or kind of a broader view of the flow as a whole, rather than following just individual particles or individual path lines for the flow itself. Okay.
So we're going, Lagrangian, it's kind of like, have you ever seen Twister?
Mhm.
Where they send up Dorothy?
Yeah. No, that's one way to think of it. Mhm. I have another analogy after this too to kind of help make it a bit more clear, but yeah, that's one way you can think about it as well. All right, any questions on this before we get into that? We get into that analogy. Okay, so one analogy I think to help make it a bit more clear, just because these definitions are a little bit dry here. Okay, so let's consider a situation, totally divorced from fluid mechanics here. So let's assume that we are, let's say a biologist, we're studying, birds, and let's say we want to study the migration of birds from one location to another. So I think as everyone knows, birds, they have the gift of flight, and so they don't have to be in the same place at any given time. And so typically certain birds, they like seasonal weather. So during certain seasons when the weather gets cold or hot, then they move from one location to another. And they usually do so in large flocks. And so they all kind of go together with all their family and buddies. Okay. So there are kind of two different ways that you can study this. Okay. So there is a kind of a Lagrangian type approach and an Eulerian type approach. Okay. So the goal of studying migration patterns is to kind of get understanding of what paths do the birds take to make their migration. How long does it take them to go? Like how many days does it take them to make that path? Where they're going actually as well, right? So under the Lagrangian approach, the way that you would do this is you would go to your flock of birds and you would tag, like you would put like a tracking collar or a tracking kind of device on individual birds. Okay. So those tracking devices probably are equipped with GPS to some degree. Maybe they're measuring other things about the birds as well. Okay. At the very least, they should have GPS. And ideally, you wouldn't just do this for a few birds. So you would try to put tracking devices on as many birds as you can. Okay. And then through that data, right, you're able to kind of take each individual path, for each bird, and then use that to glean information about the migration patterns. Okay. All right. So the Eulerian way to study migration patterns would instead be to, instead of tracking individual birds, you would set up observation stations at certain key locations, and you would look and see, how many birds pass through those locations at any given time, at any given point during the day. Okay. Right, so both different methods there will work, right? And so they'll get you kind of they'll each give you information that you need. There's just different approaches to the same thing, right? So the different description of fluid flow, same thing, right? And so you can use both the Eulerian description and the Lagrangian description. Ultimately you're going to get information about the fluid velocities and pressures and such from both descriptions. They're just kind of different ways to go about it. Okay. Just remember for this class, generally we take the Eulerian approach, right? And then from this point forward, unless I specifically state it, you can assume that we're taking the Eulerian. Okay. All right. Any questions on this so far? Lagrangian versus Eulerian? Okay. Good. All right. So expanding on that idea, expanding on the idea of the Eulerian description, let's talk a bit more in detail of the velocity field. Okay. All right, so if you look back at the definition that I gave for the Eulerian description a little bit up above, you'll see that the Eulerian description utilizes this concept of a field. Okay. Now you may have seen the concept of a field before, right? So that is a concept in multivariable calculus that should have been Calc 3 for you guys. Okay, but let's talk about it a bit. Okay. So let's start by defining what a field actually is. So a field, at least in mathematical terms, is nothing more than just a multivariable function. So it's going to be a function with multiple independent variables. So I guess more specifically, the variables in a field usually refer to, the coordinates in space. And so you have X, Y, Z coordinates and your Cartesian coordinates, as well as time. So for the most part in this class, we're going to be adopting the Cartesian coordinate system, X, Y, Z. That's pretty standard. There are some applications where you use cylindrical coordinates or spherical coordinates. We're not going to do too much with that in this class, but just be aware that that's out there as well. Just Cartesian coordinates are just kind of the simplest for us to do. Okay. All right. So in other words, another way we can say this is a field represents a quantity that can change in space and time. Okay. All right, so to kind of illustrate this, let's say we have our velocity, right? That's kind of where we started here. All right, and so our velocity field being a field variable means that it can change in x, y, z, and time. Right? So that means u is a function of x, y, z, and time. Right, so technically at any given location in the most general sense, our velocity here depends on four different variables, x, y, z, and time, right? Which is not trivial, right? A four-dimensional function is very complicated to analyze. And so there will be very few, if any, situations in this class where we actually look at all four variables. Usually we're just only considering one or maybe two variables at a time. But in the most general sense, velocity can change with all four of those variables. Okay. Okay. All right. And so if you kind of think of it in that way, right? We look at our Eulerian description, right? So remember, for our Eulerian description, we have probes at these locations. So kind of connecting these two ideas, right? Each of our probes here has a fixed location in space, right? So it has a x, y, z coordinate. Right? Let me draw a flow field going through here. Okay. Right, so each of those probes can measure things like the fluid velocity as a function of its spatial location. Okay, right. And if the velocity ever changes with time, we can observe that at each probe as well, right? So each probe can observe the fluid velocity change with time as well. Okay. All right, so that's the concept of field. The other thing that's important about the velocity field is the fact that velocity is not a scalar quantity. Velocity is actually a vector. Okay. Which makes things even more complicated because vectors are not single value. They have multiple components, okay? So that means at any given point in space, right, each point in space will have three components of velocity, the x, y, and z components. Okay. Right, so each component of the velocity is a separate variable, and then each of those velocity components can then individually depend on x, y, z, and time, right? And so you can see it kind of gets out of hand very quickly, right? So the most general description of the velocity field is the following. Okay? All right, so we have our velocity vector, right? So I put the arrow above the head to kind of denote the fact that it's a vector. All right, so our velocity vector is going to have three components, right? So it's going to have a u component. So u is going to be a function of x, y, z, and time, right? So this u here, this is the x component of velocity. And then to denote the fact that it's an x component, we're going to multiply it by I hat being the unit vector in the x direction. Plus the y component of velocity, so that's v of x, y, z, and time. Okay, j hat. So this v right here, this is the y component of velocity. Plus the z component, which we denote by w. Okay, so w is our z component. We're very rarely going to consider the z component, but I thought just since this is our first time introducing this, let's look at all three components. Okay. Right. So all this is to say that velocity is very complicated to actually describe, right? So under this Eulerian description, we have to consider changes in all three spatial variables in time, and the fact that velocity is a vector means that we have to consider all three components of the vector as well. Okay. Right. So after this, I have an example, just very simple example, just to kind of show you what a typical velocity field looks like, and then how we can plot it, how we can draw it, and then we'll move on to some other concepts from there. But before we do that example, are there any questions on this so far? Okay. All right. So let's go ahead and do a quick example here just to illustrate this. Okay. All right. So for this example, we are going to consider a 2D velocity field. So a 2D velocity field means that we're going to ignore the z component, okay? That means our velocity field is going to be, so we're going to ignore the z component of the velocity, and then we're going to ignore the z dependence on each of the components as well, okay? So this is going to be u of x, y, and t I hat plus v of x, y, and t j. Okay? Notice how there's no w, right? Because we're only in 2D, and there's no z dependence for each of the components as well. Okay. Okay. And so for this particular problem, let's say that our velocity field is equal to minus x I hat plus y j hat. All right, so that means our x component of velocity u x, y, and t is equal to minus x. And this tells us that our v of x, y, and t is equal to 1. Okay? Right, and so in this case, our x velocity only depends on x, and our y velocity only depends on 1. That's not always the case. That's just kind of this example that I'm okay. Okay. So for this example, let's just plot. So we're going to plot this velocity field in the xy plane. Okay. Okay. All right. So this is mostly just so that we can kind of visualize, just because everything up until this point was just kind of abstract math. So let's go ahead and draw our Cartesian axis here, and let's only plot the velocity field for positive values of x. All right, so we have our x-axis, our y-axis there. Okay. Okay, and let's draw several probes here, right? So remember, under the Eulerian description, we are basically observing the velocity field from these probes. Okay. Now I'm going to exaggerate the spacing just to make things a little bit easier to see, but you don't have to make things this far apart. Okay, so of course, let's observe the velocity at the origin at 0, 0. We'll observe here. So this location is 1, 0. And we'll observe here at 2, 0 here as well. Okay. All right, and then let's draw a few more points here. So let's draw one up on the y-axis. So this is 0, 1. Okay. This point right here is 1, 1. And this point right here is 2, 1. Okay. Okay, and then let's go on the negative y-axis as well. So this point here is 0, -1. This one here is 1, -1. And that point right there is going to be 2, -1. Okay. Okay, so we have 9 points here, and so we're going to draw out what the velocity vector is going to look like at each of these locations. Okay. All right, so in order to do this, all we have to do is just for each of these locations here, each of these locations has a distinct x and y coordinate, right? We're just going to take those and plug those into our velocity field and then get our x and y components of those terms. Okay. All right, so let's start with the simplest case. So let's start with 0, 0, the origin, right? So at 0, 0, at our origin, we have x is equal to 0 and y is equal to 0. Okay? So we plug that in to our velocity field, right? We plug in x is equal to 0, we get a 0 component of the x velocity, and our y component is also 0 because we have just y for that, right? So at the origin, we actually have 0 velocity. So there's nothing going on, right? Which, if you relate this to our lecture yesterday, means that we can call this a stagnation point in the flow. Remember, stagnation points are locations where our flow is 0. Okay, let's move over 1, right? So our next location here is 1, 0. Okay. So at 1, 0, our x coordinate is 1 and our y coordinate is 0. Okay, so let's plug that into our velocity field. So our velocity field is minus x for the x component and y for the y. Okay. So we plug in x is equal to 1 here, we get an x component of -1 and our y component is 0. Okay, so that gives us a horizontal vector. Looks like that. This location v is equal to -1, 0. Okay, so let's repeat the same thing at 2, 0 here. So at 2, 0, right, we plug in for our x and y into our velocity field. We get v is equal to -2, 0. Okay. So again, we have a horizontal vector, but our horizontal vector is actually increasing. It has a bigger magnitude, right? And so the way we can illustrate this usually is by a bigger arrow. Okay. All right. So now let's get off the x-axis here. So let's look at the point 1, 1. Okay. So 1, 1. That means our x coordinate is 1, our y coordinate is 1. That means our velocity vector here is going to be -1, 1. Okay. So that means we're going to have a vector that's pointing to the left, right? Because our x component is -1, and we're going to be pointing upwards because our y component is 1. Okay. So our velocity vector at this location is going to be an arrow that goes upwards just like that. Okay. All right, so the last one I'll kind of talk through, and then the rest I'll kind of just fill in, and then you guys can just copy. Let's look at the velocity at 2, 1. Okay, so at 2, 1, we have our velocity vector as -2, 1. So that's a vector again, kind of pointing diagonally upwards to the upper left, but we have a little bit more bias in the horizontal. Okay, so our velocity vector probably looks something like this. Okay. All right, so let's go ahead and fill in the rest. And so, I'll go ahead and just kind of write them in just because, talking through this just gets a little bit repetitive, but, hopefully you guys are starting to see kind of how this works. Okay. Okay. All right, so that's kind of what our velocity field looks like, at least on these 9 points, right? And of course, you could extrapolate this, and so you can plot this for even more points. And so actually, if you look at the notes, if you look at the lecture notes, I actually have the velocity field kind of printed out for more points. But just for the lecture today, I only just did 9 points there, just to kind of illustrate to you how this works. Okay. All right. Any questions on this? Okay. Good. Okay. So let's go ahead and move on. All right, so today's kind of, it's a little bit of an awkward day just because we have a lot of these kind of concepts to go through. They are kind of loosely connected to each other, but it does kind of feel like we're hopping around a bit. Okay. All right, so our next topic here is what's called the material derivative. Okay. So the material derivative, you can think of it as kind of a specialized derivative that we use in fluid mechanics. Okay. And it's meant to represent the fact that, in fluids, right, because the fluid is kind of constantly in motion, it kind of changes, the fluid velocity can change values at any given time, and it can change as it flows through space as well, okay? So the material derivative is one that kind of represents the fact that fluid properties can change in both time and space. So we're going to skip the derivation for this. And so for this, I'm just going to give you what the material derivative looks like. And then we'll kind of talk through each of the terms to kind of see what they each represent. Okay. All right, so the material derivative, and this applies for any fluid quantity, although most commonly we apply it toward the velocity, looks like the following. Okay. So for the material derivative, because it's a special derivative, we use capital D's here for instead of lowercase d's. Okay. Okay. It's given by the following. We have where v here V here can be any quantity, although traditionally this is the velocity. Okay. All right, so this is equal to we have the partial derivative of V with respect to time. Okay. We'll talk about how that derivative is different from the material derivative in a second. Okay. And then we have all these contributions that have to do with changes in space. Okay. Actually, just so it's not confusing. Apologize. Let me use a different symbol than V because we need V to symbolize the y velocity. Okay, so instead of V, let's use P. So I apologize. So if you've already kind of written it, this is kind of the change that I made here. Where I'm using P here to represent some kind of generic property or generic value within the fluid. Okay. So this material derivative can be applied to almost anything. Okay, as long as it changes within the fluid itself. Right. And of course, you can see here we have u, v, and w again. So u, v, and w are the x, y, and z components of the velocity. Let's Okay, so that is the material derivative. So you can see that, our one derivative here has kind of split into 4 different terms. Okay. Okay, so next we're going to go through each of these terms here and kind of talk about kind of what they represent. Okay. So I think from here on out, I think this class does get quite difficult just because of the fact that we're going to be throwing just a lot of different equations at you guys. A lot of them involve, integrals, derivatives, and things like that. It is very easy to kind of get lost in the sauce, lost in the details of these equations. And so, whenever I give you an equation like this, I always, what I always try to do is that, I take each term where, the details of each term and how you use them in a problem, yes, those are of course important. And so you're going to be doing those in the homeworks and the exams. But, kind of like what I mentioned on Tuesday is that, what I think is kind of more important is that you look at this equation, you kind of understand conceptually in terms of what each of these terms represent and what role they play in terms of the calculations that you're going to do. Okay, because every equation that you have, every term and every kind of variable in that expression plays an important role, and they kind of explain something physical about what's happening, in real life. Okay, so whenever you have an equation like this, I always recommend, really dissect it. Look at each term, look at each expression within the equation, and kind of ask yourself, why is this variable here? Why is this one paired together with this one? Why is this one multiplied here? Because I think then that's when you kind of really start to get a deep understanding of concepts like this. Okay, and of course that applies not just to fluid mechanics, but that applies to all your other classes as well. Okay. Okay. So for the material derivative, it's thankfully not too difficult. We have 2 different groupings here. Right? We have this term. So we'll call this term number 1. And then the next 3 terms are actually all grouped together. We'll call that grouping number 2. Okay, so let's look at the first term first, right? All right, so term number one here, this is what we call the unsteady term. Right, so the unsteady term represents the fact that fluid quantities can change with time, assuming that you're sitting at a fixed position. So you don't have to move from one location to another to observe a change in certain fluid properties. Okay. Right. And then we can think of, lots of different examples of this. Okay. So one example we can think of is, let's say that you are observing the flow of water coming out of your faucet. Okay. Right. So let's say you put a probe right at the kind of the outlet of your faucet. Okay. Now, one thing you can do is that you can increase the amount of flow that comes out, right? You can just turn the knob even more. Okay. Okay. Right. Sounds like a very simple situation, but you can think of it as like, if you're sitting on the edge of the faucet, right? You're not changing your position. You're at a totally fixed point. But there are factors or there are ways for the flow or the velocity to increase and decrease from that fixed location, right? So by turning the knob up and down, right? And of course, that's not the only way for velocity or fluid properties to change with time. But our material derivative does have to account for the fact that things can change with time at a fixed location. Okay. Okay, so that's called the unsteady term. So any kind of unsteadiness or anytime things change with time, we can account for that in that term. Okay, number two. All right, so this group of terms, right? So all of the derivatives with respect to space, right? Notice how each of those terms here is a product of a derivative with the matching velocity component. Okay, so we call these the convective terms. Okay. Convection is a concept you'll become very familiar with in heat transfer, which is the next class after this. Okay. Okay, so these convective terms represent the fact that things can change in space just by nature of flowing along with the fluid flow. So this is something that's unique to fluid flow because fluid flow we have this velocity field, and just by kind of flowing along with that flow field, things can change in space. Okay. All right. So we've already seen an example of this. Right. So we saw an example of this yesterday, actually. So if you look at our converging nozzle here, right, and we consider two different locations, we consider location A, location B, one, right? One at the inlet of the nozzle, one at the other end, right? Even if we assume completely steady conditions, right? So nothing is changing with time. As you go from location A to location B, our velocity has to increase just to make sure everything can kind of pass through the nozzle and conservation of mass is status. Right, so in a purely steady situation here with nothing kind of no unsteadiness, just by moving from one location to another, we observe a change in the velocity, right? And so that's represented by the convection term. Okay. So this concept of the material derivative is something we will return to. Again, this week is just a little bit. I mean, this lecture is just a little bit strange, just because we're doing just a lot of setup, right? So when we come back to Navier-Stokes, even tomorrow, when we introduce Reynolds transport theorem, you'll see concept of the material derivative, but so the details of how we actually use this, those are kind of yet to come. And so at this point, I would just want you guys to be more comfortable just with the concept of the material derivative, the concept of kinematics, because these are themes, these are concepts that we're going to keep returning through the summer. Okay. All right. Any questions on this? Okay. All right. So one more concept before we go to break. Let's talk about the difference between systems and control volumes. Okay. So, one thing we're trying to accomplish with this lecture notes here is, we're kind of setting ourselves up to be able to apply the conservation laws to general fluid flow. Right? And so, physical mechanics or physics, can be kind of summed up mostly in these conservation laws. We have conservation of mass, conservation of momentum, technically conservation of angular momentum as well, and conservation of energy. Right? Okay, so that's what we want, right? So we've seen a little bit already, right? So we've already kind of discussed how Bernoulli's equation is an expression of conservation of energy. We've already kind of discussed kind of an expression of conservation of mass in that context as well, right? But everything we did for Bernoulli was kind of more in a very kind of specialized case, right? So remember we kind of had to make a lot of assumptions in order to make Bernoulli's equation work, right? So under general fluid flow, where we don't make those assumptions, we still want to be able to apply our conservation laws, okay? Okay, the issue here is that, because fluid flow is constantly moving, it's difficult to apply these conservation laws because the way the traditional conservation laws are formulated, they are formulated in terms of a fixed amount of mass or a fixed amount of substance. So there's a little bit of a disconnect in terms of, how the conservation laws are mathematically formulated and, how we kind of traditionally like to describe fluid flow. Okay. Now, there wouldn't be a discrepancy if we use the Lagrangian description, right? So the Lagrangian description actually is designed specifically to apply to these conservation laws. But, just for all the reasons that we've kind of talked about already for today, the Lagrangian description is not that convenient for general fluid flow descriptions. Okay. So we need some kind of way to kind of reconcile these two ideas, right? So to kind of take our Eulerian description and still be able to apply our conservation laws to that Eulerian description. Okay. All right. So eventually, this is going to work its way up to what's called the Reynolds transport theorem, which is one of the big equations that we'll be applying for the next, probably up until middle of next week. Okay. But in order to kind of understand the Reynolds transport theorem, we have to talk about the difference between systems and control volumes in terms of what they represent. Okay. Okay. So let's start with systems. All right. So a system refers to typically a fixed amount of mass or substance of a material, and an analysis is performed on that fixed amount of mass or substance. So a systems type approach is typically what's done in solid mechanics. So in solid mechanics, you have a fixed amount of mass, let's say you have a fixed amount of concrete or a fixed amount of, metal, right? And then you analyze it from that perspective. Okay. Uh, Systems kind of work very well for solid mechanics because solids don't deform and they don't flow like fluids do. Okay. So typically a fixed amount of mass of solid will stay the same size and shape unless you kind of really mess it up. right? But as we discussed for fluids, a systems type approach is difficult to use for fluids because fluids can change shape. They can change, they can all go in different directions. And so keeping track of a fixed amount of mass, over a long period of time can be difficult because that fluid can kind of scatter to all different ways, right? So think about in this room, right? So let's say that you can use your hands to capture a fixed amount of air in your hands, right? And then you let go of your hands, right? So who knows where that air is at this point, right? Because it's kind of flowing everywhere in this classroom. Okay. Okay, so as an example, right, to kind of show you how difficult it is to take a systems approach or a Lagrangian approach to fluids, let's look at the flow of liquid through a syringe. Okay. All right, so a syringe, maybe looks something like this, right? So you have your plunger here. Right? Right, so let's say that you have your fluid inside the syringe, maybe it looks something like this. Okay. All right, so we can take a systems approach to this, right? And so under the systems approach, we're going to essentially tag and try to keep track of this fluid within the syringe as it goes through its motion. Okay. Because remember, that's the whole idea of a system is that you take a fixed amount of mass and you try to track it, all through a particular motion. Okay. So in this case, for a syringe, right, the motion is going to involve, pushing the plunger down and expelling the fluid through the syringe. Okay. So let's say we do that. Let's say that we look at our situation again where we're kind of, we have the same geometry here, right? But we push the plunger, right? So now the plunger is right here. All right, so of course that's going to push the fluid out. So you may have some fluid still stuck in the needle, right? But, that fluid is now kind of spattered all throughout just like this. And so you can see it's a lot harder to track. And so in order to kind of track that same mass of fluid, our system, right, if you think about it geometrically in terms of, the space that it occupies, it has to move with the fluid flow. Okay? Okay. So even for a relatively simple case here like this syringe, that becomes very difficult to do. Okay. right? If you want to actually see this, something in your personal life too, right? If you ever get, a coffee at like Starbucks or something like that, right? And you put cream into your coffee, right? Think of like the little package of cream you pour into your coffee. Let's see if you can kind of track and see where that cream is after you kind of mix it in. That's very difficult to do, right? Because once it kind of gets mixed and once it kind of gets everywhere, that's very difficult to do from an analysis standpoint, unless you have very sophisticated and very kind of expensive lab equipment to do. Okay. Okay. So typically the more practical thing to do, and we're going to spend quite a bit of time on this, is to do what's called a control volume analysis. Okay. So control volume analysis takes another approach where instead of trying to track a fixed amount of fluid as it goes through the flow, we're instead going to be considering a region in space, right? Most of the time, that region of space is going to be fixed. It's not going to be moving. But we can also consider cases where we have a control volume that actually moves as well. Okay? It may not move. It may not move exactly with the flow, but it moves in a way that's predictable. Okay? Now, the big difference with the control volume approach, where you don't have this issue with the systems approach, is that when you're considering a fixed region in space, right, you have to account for the fact that fluid can enter your control volume and fluid can exit your control volume. Okay, that's kind of what this last kind of point here is saying. Right. For example. Okay? All right, so let's consider our nozzle analysis that we've kind of discussed a few times already, right? So let's say we have a hose here with a nozzle at the end. All right, and so let's say that we want to analyze the flow in this nozzle here. All right, so one thing we can do is we can draw a control volume. And so let's say that we're interested specifically in the flow through the nozzle itself. So we can draw a control volume that kind of encompasses that nozzle, right? That region of space there is now fixed, right? So that's the region that we're considering. Okay. But the difference now compared to our systems approach is that fluid can enter this control volume, okay? And then fluid can leave the control volume as well. Right, so you now have this concept of an inlet and an outlet. So an inlet is a location where flow enters your control volume, and an outlet is a location where flow exits your control volume. Okay, you don't have that in the systems approach, because in the systems approach, because you're looking at a fixed amount of fluid mass, right? There's no fluid that can enter or leave a fixed amount of fluid mass because it's fixed, right? But for control volume, you do have to kind of consider the fact that fluid can enter and leave the control volume. Okay. And so, of course, the control volume approach, this is much more analogous or much closer to the Eulerian description that we've talked about already. Okay. All right. Any questions on systems and control volumes? Okay. All right, so let's take a break. We're a little bit ahead of schedule today, so let's come back at 4:30. And so what we're going to do after at 4:30 is we're going to connect these ideas of systems that control volumes through something called Reynolds transport theorem, which is going to be our central theorem for the next week or so. Okay. All right, I actually need to run to the bathroom really quickly, but then I will be back at 4:30. Okay, it's 4:30. Let's get back into it. Okay. All right. So before the break, we introduced this idea of the systems and we introduced this idea of the control volumes. Okay. So to kind of summarize, we have these systems, right? So systems refer to a fixed amount of mass or a fixed amount of substance. So systems are great because, when we apply conservation laws, they are typically applied to systems. That's just because that's just how they're defined, right? So fluid mechanics, for this class, fluid mechanics is everything, but in the grand scheme of just science in general, fluid mechanics only makes up a small portion of that. And so, it makes sense that our conservation laws were not generated or not kind of, not derived with fluids in mind. Okay? So systems are great for applying conservation laws, whereas control volumes. Control volumes are a very natural and very kind of convenient way to analyze fluid flow. Right. And so we want to reconcile these two ideas because we want to apply conservation laws to fluids, but we want to do so from a control volume perspective where it's kind of easier to kind of keep track of things and compute what we want. Okay. So that leads us to the development of one of the most important theorems for this class, which is called Reynolds transport theorem, or RTT. Okay. So Reynolds transport theorem essentially gives us a framework, right? So it's called a theorem technically, but I want you guys to think of it as kind of like a framework which we can use to apply conservation laws to fluid mechanics scenarios. So to actually explain this, we're actually going to start with an analogy because I think that kind of helps illustrate this. And this analogy actually is you can actually compare it kind of one to one with Reynolds transport. It's actually really convenient. So let's look at a bank account. It can be your bank account, or it could be a bank account. Doesn't really matter. Okay. Okay, so a bank account, this is something that we all use to store our cash, right, or keep track of our money. Okay. Okay. All right. So in this situation, the bank account itself, you can think of that as your control volume. Whereas the money, right, we're not really going to think of the money as the system, but we're going to think of money as kind of the substance or the mass that we are keeping track of going into and out of our control volume. Okay. It's stuff. Okay, so from your bank account, you can do any number of actions with regards to your money, right? And so on the one hand, usually the happy thing that occurs to your bank account is you can deposit money into your bank account. Another thing you can do is you can withdraw money, right? You can take money out. Okay. Right, and there's actually a third thing that can happen within your bank account that can generate money for you. Most of the time, it's negligible. But if you deposit your money in, let's say, a high yield savings account, you can generate interest, or your bank account will generate interest that will give you money based on the amount of money that you have in there already. Okay. So for instance, if your bank gives you a 5% APY, for instance, then the bank will deposit into your bank account 5% of whatever you had in your bank account, as kind of a you can almost think of it as kind of like a payment for using their services. Okay. Or what that the bank is paying you. Because in reality, your bank doesn't just store your money into a vault. They take your money and they invest it in other stuff and they earn returns. And so that's part of their returns to you. 5% is very generous. It's very difficult to find 5% nowadays for a savings account. But let's just take that number. Okay. Okay. So all of these actions, the reason I list these three these are the typical actions that can occur that can affect the balance of your bank account. Okay. And in fact, we can relate these in a simple equation. Okay. And so our equation that we can write, we can take our bank account balance. Right? Whatever our current balance in our bank account is a result of these three particular actions here. Okay. Okay. So our bank account balance at any given time is equal to the interest that we generate plus the money that we deposit in minus the money that we withdraw from the bank account. Okay. Okay. All right, so I want you guys to keep this analogy in mind because we're going to develop Reynolds transport theorem. We're going to kind of skip the traditional kind of mathematical derivation. We're going to instead kind of motivate it and kind of explain it based on this analogy right here. Okay, so keep this in mind because you're going to see that there's kind of actually a one-to-one correlation between the terms in our Reynolds transport theorem and this kind of very kind of simple kind of bank account analogy. Okay. Okay. All right. So coming back to fluids, right? Let's now consider the control volume around a arbitrary, section of fluid flow. All right, so let's say that we have fluid flow coming like this. Actually, let's make it a little bit simpler. Let's consider this to be pipe flow, so that we just have a distinct inlet and a distinct outlet. I apologize. Okay. So let's consider a flow to pipe. Let's draw a control volume within that pipe. Right, so you'll see me use the shortened form CV. So CV stands for control volume. Okay. All right. So the reason I kind of switched to the pipe here is because for a pipe, we have a very clear region where flow is entering the pipe and a very clear region where flow is exiting the pipe, and the lateral walls we're not going to have any flow past them. All right. So for instance, if you have flow coming in from the left to the right, right, we have a very clear inlet face, a very clear outlet face, right? And flow is kind of progressing through the control volume in that sense right there. Okay. Okay. All right. So now that we have our control volume here, what we're interested in formulating mathematically is we want to get an expression for the rate of change of some extensive property progressing through that control volume. All right, so I'm using the capital symbol B. So B here is just going to be some generic extensive property. Okay. Because the thing with the material with the thing with Reynolds transport theorem, very similar to our material derivative, is that we can apply Reynolds transport theorem to any number of extensive properties. And so we're going to apply it to, let's say B represents the mass of fluid, maybe B represents the momentum of fluid, maybe B represents the total energy, right? So remember, we're trying to come up with a vehicle, we're trying to come up with a framework for us to apply our traditional conservation laws to fluid mechanics, okay? And so B here can represent any kind of extensive property. Okay. But we'll leave it generic here just because, we're gonna, we want to come up with a generic Reynolds transport theorem and apply it to everything. Okay. Okay. So mathematically, what we're looking to determine here is an expression for partial B within the control volume, partial T. Okay. Right. So I'm using partial derivatives here because, B here is going to depend on multiple variables, not just time. Right? But this here represents the rate of change of B within the control volume, right? So that's why I give that subscript. Right? So partial B, CV, partial T, right? So the rate of change of B within the control. right? And so if you're talking from a physical standpoint, right? So for any extensive property B, right, there are generally three different ways that B can change within a control volume. Okay. Right, number one, right? Number one is that B can flow into the control volume with the fluid. Right? So if B is mass, right, and fluid is flowing into the control volume, then there's mass obviously coming into the control volume at the end. Okay? By similar token, right, B can also leave the control volume via an outflow. Right, and then the number three way that the quantity of B can change within the control volume is, let's say that there's some mechanism for B to be either generated or consumed within the control volume itself. Second. So in this case, those will be cases where B represent things like energy, right? So you could heat up the fluid in there. So by heating the fluid in there, then you're adding energy into the system. Yeah. Or if B is momentum, then you can apply an external force that's going to generate momentum in the fluid. Okay. Right. So hopefully this should look familiar because these are, very similar to the ways that our bank account balance can change as well, right? So inflow represents kind of the same thing as deposits. Outflow represents the same thing as withdrawals. And then generation or consumption of B, that is essentially the same thing as interest, right? So we can come up with the same mathematical relationship, okay? Where, if we call this first term up here, this partial BCB partial T, we call this accumulation. We could come up with a mathematical expression for the accumulation of B within a control volume. Okay. All right, so we can basically say that accumulation is equal to inflow minus outflow plus generation slash consumption. Okay? And of course, if we have consumption, then we have a minus sign, but generally speaking, we'll just have a plus sign there. Okay. All right, and then finally, what we can do. So now that we kind of see the the motivation or kind of where this comes from, we can finally put some mathematical variables in terms to all of these expressions here. Okay. Okay. So I'm going to give you just kind of the raw mathematical expressions for these, and we'll go through and explain each one, just like we did with the material. All right, so for accumulation, we already know what that looks like, right? So accumulation is the partial derivative of B CV dt. Okay. So that's the accumulation of B within the control volume itself. Okay. All right, next we have the inflow term. So inflow is given by the following. we have rho inflow multiplied by area at the inflow multiplied by the velocity at the inflow multiplied by b the inflow. Okay. So that right there is our inflow term, and I will explain each variable in that expression right after this, don't worry. So let's write out the entire Reynolds transport theorem first, and then we'll go through what each of the variables mean. Okay. Okay. Then from that, we're going to subtract our outflow. So our outflow term is going to look very similar, except we're going to have a minus sign. Okay. So you have rho at the outflow times cross-sectional area at the outflow, velocity at the outflow, and little b at the outflow as well. Okay. And then finally, we have the generation consumption term. Okay. All right, and so this is kind of where our material derivative comes into play, although we're not going to actually use it in this material derivative form. We're going to actually use it to kind of represent something else. Okay. But to represent the generation or consumption of our quantity within the control volume, we're going to use our material derivative, okay, with one very key distinction. Okay, so we're going to use a material derivative to represent generation and consumption. Okay, but the key difference here, we just use the material derivative just because that's just mathematically how it's defined. But the one thing I want you guys to pay attention to is note the difference in the subscript for B. Okay, whereas on the left-hand side for accumulation we have CV as our subscript. Okay, or the generation accumulation term we instead have the system at the subscript. And so it's very subtle, but it's actually a very important difference because, right? Because that last term there is defined on the system, right? This is where our conservation laws can be applied. Right? Right. So that right there, this is at least a simple form for Reynolds transport theorem. All right, so this is a simple form for Reynolds transport theorem with just a single inlet and a single outlet. We'll go over the more generic form after this, but I do want to go through and explain each of the terms in this expression first. Okay, but now that we've kind of written this kind of overall term here, let's explain the variables. Okay. Okay. So I think the term here with the most unknown variables are the inflow and outflow. Let's describe those two. Okay. So first we have rho, right? So rho should be a familiar character. This represents the density of the fluid. So technically, we account for the fact that density can technically change from the inlet to the outlet. It's very uncommon. So, most of the times we're considering an incompressible fluid. So density is constant, but technically this Reynolds transport theorem doesn't make an assumption for that. Okay, so technically you can have different densities at the inlet and outlet. Okay. Okay. Next, we have A. So A here represents the same cross-sectional area that we use for Bernoulli's equation. Okay. Right, so this can be different inlet and outlet, and in general, actually, they are different. So this is the cross-sectional area for the inlet or outlet region. Okay. Right. V here is the velocity. Okay. So that's the velocity of the fluid carrying our quantity into the control volume or out of it. Okay. And in general, that can also be different at inlet and outlet. Okay. So the only one that we technically assume is the same most of the time at inlet and outlet is the density, right? But the cross-sectional area and velocity can be different. And you'll see that kind of once we start to do examples, and we'll probably do some tomorrow after the midterm. Okay. All right. And of course, we have little b here. So little b here is the intensive version of our extensive property, capital P. In other words, you can think of little b as big B per mass. Okay. Or in other words, little b is equal to big B divided by M. Okay. All right, so that's generally the idea of Reynolds transport theorem, right? And so if you have some kind of property that you want to analyze within a control volume, you just apply Reynolds transport theorem to it, you compute each of the terms, okay? And then that will give you an equation that you can use to analyze your system, okay? Now, we're not going to do too much today just because, this is one of those things where the devil's in the details. And so, tomorrow after the midterm, we'll start by applying this conservation of mass. That's kind of the simplest thing we can do. And then next week, we'll apply this to conservation of momentum, conservation of energy, and if we have time, we'll do conservation of angular momentum as well. But that gets a little bit too complicated. It's more just for if you like that stuff. Okay. Okay, well, let's do just a very quick example just to kind of illustrate this first. Okay, so let's do a control volume analysis of the amount of fire, the amount of, the word is escaping me, the amount of fluid that comes out of a fire extinguisher. Okay. All right, so if we draw our fire extinguisher, so let's say we have our nozzle up here, and our fire extinguisher just like that. Okay. All right, so our fire extinguisher fluid will assume it had a density of rho, which is known. Okay. Okay. We're also going to assume that we know the cross-sectional area of the outlet nozzle here. Okay. So this area right here, we're going to assume has a known area. We'll call it cross-sectional area A. Okay. There's no numbers on this problem here. We're just going to show just how to apply Reynolds transport. So everything's going to be terms of variables. Okay. All right, and let's say that based on the specifications of this particular fire extinguisher, let's say that we know once we kind of push down the lever, we know the velocity of the fluid that's coming out as well. Okay. So in this situation, let's say that we are kind of expelling from the fire extinguisher. So, we're kind of pushing the button to expel it to extinguish fire, right? So what we want to do is let's use Reynolds transport here. Let's use Reynolds transport theorem to compute the rate at which the mass of the fluid within the extinguisher decreases as a function of time. All right, so very simple application of Reynolds transport in this case. Okay, you're going to see the result is very straightforward. But I think it's good to kind of go through the whole motions to kind of see how Reynolds transport is applied here. All right, any questions on just the setup for this example here? Okay. All right, so let's go ahead and do our analysis. Okay. All right, so the first step, whenever you do any kind of Reynolds transport theorem analysis or any control volume analysis, is you need to draw your control volume. Okay. So sometimes it'll be obvious in terms of how you should draw your control volume. Some problems will draw your control volume for you. Okay. And so what we're going to discuss at the end of class today is just general tips in terms of how you should draw your control volumes. So there is an art to it, and there are good control volumes and bad control volumes. Okay. So for this one, it's fairly straightforward. So we're going to draw a control volume that encompasses the entire fire extinguisher. Okay. Okay. Luckily, this is a fixed control volume. In other words, its shape and its size is not changing with time. Okay, so the fire extinguisher itself does not change with time as well. Okay. Okay. One thing you should always note whenever you draw your control volume is to make note of where all of the inlets and outlets are in your analysis. Okay. There are going to be situations where you're going to have multiple inlets and multiple outlets. Sometimes you're not going to have any inlet or you're not going to have any outlet. The inlets and outlets are very important to identify because that's where a lot of the action, a lot of the terms in Reynolds transport theorem will take place. Okay. Now, for this fire extinguisher, we're not refilling the fire extinguisher; we're only expelling it. And so in this case, we have no inlet. Right, so we're not putting fluid back into the fire extinguisher here, and we only have one outlet. Okay. The outlet, of course, being the nozzle of the fire extinguisher. All right, so that simplifies our life a little bit. So when we apply Reynolds transport theorem, knowing that there's no inlet in this problem means that any term that involves the inlet, we can just kind of cross it out because it's not going to be relevant in this case. Okay. Okay. Next step. All right, so next step in the analysis process is to first figure out what quantity our extensive quantity is going to be, okay, and then plug that into our Reynolds transport theorem. Because that's going to define our whatever quantity for B that we're plugging in. Okay. Okay, so for this, usually you have to go back to this problem statement, although for the most part, these are fairly obvious. Okay. All right, so for this particular problem, we're interested in computing the rate of change in which mass is leaving the control volume section. Okay. So that tells us that, when we apply Reynolds transport theorem, we're going to set capital B equal to mass. Okay. So with that in mind, let's go ahead and do that. So if we set big B equal to mass, that means little b, right? So little b is the intensive version of big B, right? So little b is equal to big B divided by mass. But if big B is mass, right, that means little b is just mass divided by mass. And so little b in this case has to be 1. Okay. Okay. Now, another thing we can do at this step here is we can specify what our generation and consumption term looks like. Okay. Okay. Remember, what we said before is that material derivative term, that's where we're going to apply our conservation laws. Okay. Okay, so in this case, if B is mass, right? Okay. Right, so for this problem, if big B is mass, we want to find out, or we want to kind of infer what the production or consumption of mass is within a fixed system. Right? But by definition, of a system is a fixed amount of mass, right? And so the production or consumption of mass in a fixed amount of mass is, well, it's kind of it's impossible, right? So you can't generate more mass in a fixed amount of mass, right? And in fact, that's what the conservation of mass tells us. So conservation of mass tells us that it cannot spontaneously generate or destroy mass in our universe, at least what we understand of it. And so that means our production term here is going to be equal to 0. Okay? So conservation of mass is kind of what we're going to start with. We're kind of getting a head start in it already, and just because we're a little bit ahead of schedule, I am kind of giving a bit more details here. So this is a little bit of a preview in terms of what we're going to do tomorrow after the midterm. Okay. But basically, when we apply conservation of mass, our production and consumption term is equal to 0. Okay, making it a bit simple. Okay, good. All right, so now that we have all that stuff, let's go ahead and plug it finally all into our Reynolds transport theorem. Okay. Okay, so I'm going to write just the generic form for Reynolds transport first, and then we will apply it to this problem. Okay, so general Reynolds transport is partial BCV partial T is equal to rho at the inlet, A at the inlet, velocity at the inlet, times B at the inlet, minus same things at the outlet, plus our generation term. Okay. So let's apply everything that we know about this problem already. All right, so we know from this problem, based on what we've discovered already, that there's no inlet for this problem. All right, so since there's no inlet, we can go ahead and cross out that first term. We also know that there's no generation just because of conservation of mass and just what we set our B quantity equal. Okay. We also know, based on our definition for capital B, that little b here is just 1. And the mass per mass is just 1. Okay. And in fact, everything else here we know already because we know we're given from the problem that we know the cross-sectional area of that outlet nozzle, we know the density, and we know the velocity of fluid that's coming out as well. Okay, so we plug all that in, and what we get is partial mCv, partial T, okay? Which remember, this represents the accumulation of mass within the control volume. Well, in this case, there's no accumulation because mass is actually leaving. So you can think of this as the depletion as well. Okay, so accumulation / depletion. Okay. All right, this is equal to. We just plug in all those quantities, although in this case we're doing everything in terms of symbols. We have rho times A times the velocity. Okay, and so this tells us that the rate at which the fluid, or the rate at which mass within the fire extinguisher is being depleted is equal to the product of the fluid density, the cross-sectional area, and the velocity of the fluid coming out. Okay. All right. So very, very simple case, but we're going to be following that same process, for the next, couple of lectures, and so it's good to get familiar with that. Okay, especially because we're going to be applying this to more complex cases in the future as well. All right, any questions on this example and the application of Reynolds transport theorem for these types of problems? Okay. All right, so to finish off the lecture today, I do have a couple kind of miscellaneous topics here. Okay. Well, next one's actually kind of important. But the next one is what we call the general form of Reynolds transport. Okay. So the previous form of Reynolds transport that we just discussed is good if you have a single inlet and a single outlet. In general, you could have multiple inlets and you could have multiple outlets. And so we need a more general form for Reynolds transport. Okay. So the same idea is going to apply, right? And so all our terms are going to be the same. It's just that they're going to take a different mathematical form in this more general form. Okay. All right, so I will say this form does look a bit more intimidating, but just think back to our bank account analogy, and so and we're going to use that to relate each of the terms here. Okay. Okay. So the general form looks like the following: we have partial t of integral rho times b dv. Okay. So that's integral over the volume. This is equal to. Next term is the same. This is our production term. Okay, so we have the material derivative of our extensive property with respect to time minus, we call this our flux term. So this accounts for both the inflows and the outflows. Okay. So you have integral of rho times b multiplied by our velocity vector multiplied by our normal vector, okay, dA. Okay. So I know this looks a bit more intimidating with the integrals there, but don't worry. This form, if you apply to a very simple case, you get back our other form of Reynolds transform. Okay. Okay. So just like we did before, let's go ahead and label each of these terms here. Okay. All right. So the first one we have here, this is our accumulation term. Okay. Right. So it's just in different form, right? And so this accounts for the fact that we may have differences in V at different locations within the control volume. That's why we have that integral there. Okay. Next, we have the material derivative. So this is the same. So this is our production / consumption term. Okay. And remember, our production consumption term, that's applied onto a system, right? So traditionally, this is where we're going to apply our conservation laws. Okay, so just like in the previous problem, we set that production term equal to 0. And then once we're considering things like momentum and energy, then we'll account for that there as well. Okay. All right, and then finally we have this last term here. This last integral here, this accounts for the inflows and outflows. And so this has a more generic name. This is typically known as a flux integral. Okay. So anytime you have a quantity that's either entering or leaving a control volume, we call that in general, we call that a flux. Okay. So mathematically, we can put it into a single term, a single integral, and we call that the flux term. Okay. Now, the way that we apply this is that, this flux term often splits up into multiple different terms, depending on how many inlets and outlets that we have. Okay. And most of the time, that term there just ends up being a product of rho times b times a times the velocity, just like in the previous form, right? But this accounts for the fact that if we have multiple inlets, multiple outlets, or no inlets and no outlets, then this that. Yeah. Okay. So the actual details in terms of how we actually plug into this form, we'll leave that for the next lecture. But I at least wanted to show you the generic form here. Okay. All right. So a couple details here. Okay. So one kind of smaller detail is that the way that I've shown you the Reynolds transport. This is this kind of accounts for, or it relates back to our bank account analogy. But sometimes Reynolds transport theorem is actually represented with the production term by itself. And what I mean by that is that the material derivative, we just move that to one side of the equal sign, so it just kind of binds. Okay. So all this is just an algebraic manipulation. All we did was just we moved the flux integral to the other side of the equation. Right? So don't get confused if you see this form of Reynolds transport. It's exactly the same. It's just that we just move the terms around a little bit. Okay. So some textbooks and some people prefer this form here just because there's no minus sign. People just don't like minus signs in their equations. So just be aware of it, right? So this kind of a minor point, but so just be aware of kind of where all the terms are in the equation. Okay. Okay. So that's one point I wanted to make, right? So especially I think if you're reading the textbook, I think the textbook prefers this form right here. Okay. The other point I wanted to make here is expanding on the flux term a little bit and talking about this term right here. Okay. Okay. So that term that I've underlined there is a dot product between the velocity and n hat, where n hat is what we call the normal. All right, so most of the time, so seeing a dot product there is a little bit scary, right? Because, technically a dot product, if you write it out, is actually, typically the magnitude of the velocity multiplied by the magnitude of the normal vector cosine of the angle between them, right? So that's just kind of our typical dot product formula. Okay. But usually, when you're applying Reynolds transport theorem, remember, you have freedom to choose your control volume, right? So most of the times you're going to choose your control volume in a way such that when you compute this dot product, it's convenient. Okay. Right. And so what I mean by that is that try to draw your control volume such that your velocity vector and your normal vector are parallel to each other. Okay. That's the most convenient because then you don't have to worry about any kind of angle or cosine shenanigans. Okay. You know what? I've kind of talked about that. We haven't discussed what the normal vector is, right? So that normal vector, And maybe probably I should have started with that. Okay. So this normal vector here is a vector that points outward from your control volume, right? So basically, whenever you have your control volume, the normal vector is a vector that points outward, normal to that surface. Okay. Okay. All right, so if you have your control volume, let's say your control volume looks like the following. So every exterior surface of your control volume has a normal vector that's associated with it. Okay. Okay, and remember, the normal vector always points outwards, right? And the reason it's called the normal vector is that it is normal to your surface. Okay? So for instance, on this surface right here, your control volume is a vector that points outward to the right. It's normal to your surface, and it's points in that direction. Okay? On the upper surface, we have a normal vector like that. Okay? Bottom surface, we have a normal vector that points downwards. And on the left-hand side, we have a normal vector that points outwards just like that. Okay. Okay. All right, so you can see that, based on how you draw your control volume, you can control the direction of the normal vector, right? And you want to draw your normal vector, you want to draw your control volumes in a way such that your normal vector and your velocity vector, they are parallel, okay? Okay, now there are two different cases. So let's assume now that you've drawn your control volume in a way such that your velocity and your normal vector are parallel to each other, okay? Okay. So you can have two vectors that are parallel, so they could be pointing literally in the same direction, or they can be what's called anti-parallel, which means that one's pointing in one direction and the other one's pointing in the other direction, but they're still technically parallel, so they're never going to meet. Okay? And so that corresponds, at least in our control volume cases, to cases where flow is entering the control volume and where flow is leaving the control volume. Okay? Okay, so let's look at what those look like kind of visually. Okay? Okay, so let's look at a case where your flow is entering the control volume. Okay. Okay, so let's say we have our control volume surface just like this. Okay. We have our normal vector. And our normal vector always points outwards, right? And so we're assuming that our control volume is to the right of our red dotted line. Okay. Okay. And let's say that we've drawn our control volume in a way such that our velocity is parallel to it, but our velocity and our normal vector are opposite directions, okay? Because our normal vector points out, but our velocity is going in, okay? All right, in this case, what happens when you take the dot product between these two quantities here? So when you take the dot product of two vectors that are in opposite directions, okay? Essentially, the angle between them is 180 degrees, okay? Right? And so that means if the angle between them is 180, you go back to our generic dot product formula up here, okay? Cosine of 180 here is minus minus 1. So that means when you take the dot product of a velocity vector at the inlet face, then you get a negative number. Okay. Right. And so in other words, we can say that for all the inflows, right, when we compute the flux integral at those inflows, we're going to get a negative, we should get a negative term, a negative number. Okay. Which is counterintuitive, right? So when you think of inflows, you think of deposits into your bank account, right? And so it's a little bit counterintuitive to think of inflows as having a negative sum. Okay. But if you look back at our generic form for our Reynolds transport, you'll see that there's this negative out in front of the flux term, right? And so because of that negative, then if we have a negative for the inlet because of the dot product, then that's going to cancel that out. Okay. Okay. And of course, the opposite is true for outflows, right? And so if we look at the same situation for flow leaving for CV, okay. Okay, so we have our normal vector here. Now it's pointing to the right because now we're at the outlet face. Okay. We have our velocity. Okay, our velocity is crossing our control volume, but this time it's leaving the control volume, right? So now n hat and our velocity are in the same direction. Okay, now when you take their dot product, now you can take this dot product, you get a positive number. Okay. So that means when you compute the flux integrals for outflows, you're going to get a positive number. Okay. All right. Any questions on that dot product quantity there? Okay. One other comment I'll make on the dot product, and then we'll wrap this up with some tips and tricks. Okay. All right. So one other thing about this n hat vector, so we've kind of already discussed in terms of what direction that it faces. Okay. Another important or another very interesting quantity about this n hat vector is that it is what we call a unit vector. Now, unit vectors are very unique, and the reason we call it a unit vector is because it has magnitude of 1 or length 1. Right? So if we take the magnitude of the unit vector, we just get 1. All right, so unit vectors are very useful, right? So no doubt you've seen a unit vector in one of your previous either math or physics courses. Okay. So unit vectors are mostly just used to denote direction, right? And so they're not meant to alter any kind of magnitudes or anything like that. Okay. All right. So that affects our calculations because when we take the dot product of the velocity and the unit vector, right? The magnitude of what we obtain should be the same as the velocity magnitude. Okay. Right. So for both of these cases, right? So when we take the dot product between our velocity vector and our normal vector, we should just get the magnitude of our velocity, okay? And so the normal vector does not affect the magnitude of that calculation at all, okay? The only thing that's in question here, the only thing that we have yet to determine is the sign of that, right? So for inflows, remember you put a negative sign. For outflows, you put a positive sign. Okay, good. All right, and so just like I mentioned, over the next couple of lectures, starting tomorrow after the midterm, we'll be applying Reynolds transport theorem to several different fluid properties and seeing how those calculations go. Okay, so we'll start with mass. Mass is the simplest one, and then next week we'll get into things like momentum and energy. Okay. All right, but before we go today, I wanted to leave you guys with some tricks in terms of how do we even select a good control law. So this is one thing I think is taken for granted because a lot of the problems we're going to do in this class, usually it's pretty obvious in terms of what your control volume should be, or sometimes the problem even drawn for you already. Okay. But if you're going to be using this technique out in practice, out in the real world, right? Sometimes it's not so obvious where you should draw your control volume, right? And so it's good to kind of think about what are some best practices or what are best ways to do this to make your analysis a little bit easier. Okay. Okay. All right. So the first tip we've already discussed here. So the first tip is to make sure that the boundaries of your control volume, wherever you have your inlets and outlets, your boundaries are perpendicular to the velocity vectors. Okay. All right. And so if you have a flow in a pipe like this, right? We know the flow is going along the direction of the pipe. So a good control volume, knowing that the flow is going horizontal like this, a good control volume will be something like this. Okay. We can see here the boundaries on the left-hand side, the boundaries on the right-hand side are perpendicular to the flow. And so that makes the dot product easy to do. Okay. So this is a good CV. Okay, so a bad CV, let's look at the same situation. Okay. So we have flow in a pipe, and so we know the flow is going from left to right. A bad CV would look like the following, right? So maybe you're cutting your control volume at a bias like this, right? And so your normal vector and your velocity vector are not perfectly aligned. So when you compute your dot product, it's going to be a little bit annoying because you have to have that cosine term there. Okay. Or you make it even worse, right? And so let's say that you have a boundary that kind of changes shape, like that. Now that the right side there is really a mess because now your direction is not constant, right? And so you're gonna have to integrate that. That integral becomes a lot more complicated. Okay? Right. So try to draw your control volume so that they're perpendicular to the velocity. Okay. Now along that same token, so technically this is still part of the same tip. So we'll call this tip 1A. Okay. This is not really going to apply to this class because, again, in this class, mostly we're going to consider fairly simple flow situations. But if you have a flow situation where you have very complex flow that's going in all different directions, right? Try to draw the boundaries of your control volume try to put it in a location where your flow is the simplest. Okay. So don't make your life harder on yourself. You may have a situation where your flow is doing some kind of chaotic stuff, right? And so you don't want to make your life more difficult by making your control volume difficult as well. Okay. Okay. So one quick example I can give here is, let's say that you're computing the flow inside a combustion chamber. Right? So inside a combustion chamber is a very complex phenomenon, right? So you have a combustion reaction taking place. You have some thermodynamic and chemistry and stuff going on. Okay. You want to draw your control volume so that it's kind of as simple as can be. All right. And so for instance, let's say your combustion chamber looks like the following, right? So you have kind of multiple inlets here. Okay. Right. So an example of a bad control volume might be something like this, right? So maybe you draw kind of a box that's like this. Right? So you have flow that's coming in, you don't really know where it's coming in from, right? So you have flow passing through all the boundaries. Okay? So this would be a bad CV. Right? Right? So a good CV, will probably look something like this, where we take advantage and we know where all the inlets are, right? So maybe we contour the control volume with those walls right there, right? So that way we know exactly where the flow is coming in from, right? So that we can kind of better analyze the flow this month. Okay. So again, that last piece of advice probably not going to apply in this class, but just good to keep in mind in general. Okay. Okay. Tip number 2. Okay. Okay. So tip number 2 also has to do with the boundaries of your control volume. Okay. And so usually when you're doing this type of analysis, you're interested in computing things like velocity or pressure at certain key locations. Okay. The thing with control volume analysis is that we can only really compute fluid properties at the boundaries of our control volume. And so if you're interested in a quantity at a particular location, try to put your control volume boundary at that location. And the reason for that is that when we apply Reynolds transport theorem to our flow quantities, it's, you'll see that most of the time we're computing things at the boundaries of our control volumes. Okay. Okay. So as an example, right? So let's say we have a pipe flow here. So let's say that we're interested in, for some reason, let's say that we really want to know the velocity of the flow at this location. Okay, so this location right here, this is a location of interest. Okay, so don't draw your control volumes, right? Don't draw your control volumes so your location of interest is somewhere on the interior, right? So this does you no favors, right? So there's in fact no way to actually compute this. Instead, draw your control volume so that one of your boundaries aligns with that location of interest. So that's tip number two. So tip number two is whenever you have a location of interest, put the boundaries of your control volume at that location. Okay. Okay. Last tip that we'll mention here. This one I'll just kind of mention just because this is another one where the devil's in the details. But tip number 3 is don't be afraid to use a moving control volume or a deforming control volume. Right, so we're going to do some problems, probably not tomorrow, but probably next week with moving control volumes, okay, and deforming control volumes. So don't be afraid of them. I know it's when you see your first problem with the moving control volume, it's going to be very intimidating. I get it. It's a lot going on, but you'll see that once you kind of get used to it, that it's some problems are just much more naturally solved with the moving control volume versus if you try to do it with a static. So the temptation always is to try to find a static control volume for your problem, but that's not always going to be the most convenient thing, believe it or not. Okay. So part of this tip here is to just recognize situations where maybe a moving control volume would work out better, and don't be afraid to make those differences. Okay. Now, when you use a moving or deforming control volume, it does change your Reynolds transport a little bit. But don't be afraid to do so. Okay. All right, but that's one we'll get into kind of more probably next week. All right, any questions on this before we wrap it up for today? Okay, all right, so that's all we got time for today, and so I will see you guys all tomorrow for the exam. If you have final questions before the exam, don't be afraid to email me. So I'll be available all morning tomorrow to answer questions. If you can't make it to office hours tomorrow and you want to meet up to discuss something, just let me know. I usually don't come to the office until after lunch, and so if you do want to meet with me in the morning, it'll probably be what we'll do. Okay, but don't be afraid to do so. I'm available all morning tomorrow. Okay, all right. So best of luck studying tonight. If you have any last minute questions, let me know. Solutions for homework 2 will go up before I go to bed today. And yeah, I'll see you guys all tomorrow. Yeah, if not, perfect. Thank you. Yeah. See you tomorrow. Yeah, tomorrow.
So for material derivative, it's part of the
Actually, it's a good observation. It's the gradient of the dot product with the velocity movements.
But when you're adding the time derivative with your spatial,
Exactly.
wouldn't your dimensions not be consistent?
So in this case, remember, we're multiplying by the velocity. So
Oh.
remember, velocity is length over time. So the
Mhm.
lengths cancel out and you get same dimensions.
Okay, with your, from this one.
Exactly.
Reynolds transport. When we say your boundary, that's only for 2D cases. Or
So it technically applies for 3D as well, but for this class, we're only going to consider 2D. Yeah, 3D is hard to
you
draw.
would do like a line or go, right? It's 3D for your flux.
So actually, that's a good point. So this flux term right here. This flux term, technically it's an area integral, but for 2D, it's technically a line integral. You're right. But we're actually not going to integrate in this class because in this class, everything there's going to be a constant, and so it's just going to be arithmetic basically. But you're right. Technically, in the general case, 2D that turned into a line integral. 3D that's a surface integral.
And you can convert that surface to like just do divergence theorem or
Exactly.
theorem.
Yep, exactly. Yep.
Because in this class we're just doing like normal flow, but if you get like the bad flow, then you kind of have to apply the
Exactly, yeah.
Newton's theorem.
Exactly, yeah. Especially if you have flow. So so for a lot of this class, when we apply Reynolds transport, we're essentially going to be assuming that the velocity is constant across this boundary. But in reality, that's actually not the case. So the velocity is going to be changing in space, and so you would actually have to perform that way.
Thank you.
Mhm.
I like this class. It's
Are you
fun.
good? It's good.
I like the application of of calculators.
That's good.
I think it's interesting.
That's good. That's good.
Yeah.
I'm glad to hear that. Glad to hear that.
It was like very abstract.
Yeah.
Calculating when you go through like electromagnetism and fluids, I think it's like super interesting.
Yeah.
When you-
No, for sure. Yeah.
when you go through the line integrals and stuff.
Yeah.
It's
Yeah.
pretty cool.
That's good. That's good. I'm glad you're enjoying it.
Thank you.
Yep.